We are live now.
Good afternoon all. Welcome you back to ICDAMS2020 conducted by SSC SIMATS. Hope you had a very informative session in the forenoon. We appreciate all for joining us in the afternoon session, which I bet you it's going to be more interactive and fact-loaded. Now, I request Dr. Szekely, convener of ICDAMS2020, to welcome the speaker. Sir, please.
Good afternoon, one and all. On behalf of ICDAMS2020 Organizing Committee, I welcome Professor Dr. Szekely, Advanced Membrane and Porous Material Center, King Abdullah University of Science and Technology, Kingdom of Saudi Arabia, to deliver his keynote address. Thank you, sir.
Thank you for the introduction, and thank you for...
Yeah, just a minute. Let me quickly read your profile. Very good afternoon to all of you. I am Dr. Deepak, Associate Dean, Saveetha School of Engineering, Saveetha Institute of Medical and Technical Sciences. I take this opportunity to read out the profile of Dr. Gyorgy Szekely. Dr. Gyorgy Szekely is currently working in Advanced Membranes and Porous Materials Center, KAUST, Saudi Arabia. Professor Szekely received his M.Eng in Chemical Engineering from Technical University of Budapest. He earned his PhD degree in chemistry under the European Commission's Marie Curie actions from the Technical University of Dortmund, Germany. He worked as early stage researcher in Hawaiian Pharmacy Science Limited, Portugal, and an IAEF in Tokyo, Japan. And the lecturer in chemical engineering at the University of Manchester, UK. Professor Szekely was a recipient of the Distinguished Visiting Fellowship of the Royal Academy of Engineering. He is currently working in chemical engineering at the Advanced Membranes and Porous Materials Center at King Abdullah University of Science and Technology, Saudi Arabia, and a visiting academic at the University of Manchester, UK. His multidisciplinary background covers the design, fabrication, and applications of membranes and absorbents with the particular focus on green and sustainable chemistry and engineering. He serves as an academic editor for the journals Advances in Polymer Technology, Advanced Material Letters, Current Nanomaterials, and the Separation Process section of Frontiers in Chemical Engineering. He is member of the Royal Society of Chemistry and a fellow of Higher Education Academy. He has published over 60 articles, 5 patents, and 5 book chapters, and edited 2 books. In the past, he visited Saveetha School of Engineering and conducted credit course titled Advanced Materials for the students of Mechanical and Civil Engineering. Myself and Dr. Gyorgy were also involved in collaborative research work on water filtration. I am very happy to welcome Dr. Gyorgy Szekely to deliver his invited talk in the 4th International Conference ICDAMS2020. He will be addressing on the topic Robust Polymer Materials for Nano Filtration Process. I'm very happy once again to welcome Dr. Gyorgy. Over to you, Dr. Gyorgy.
Thank you, Dr. Deepak. Thank you for the introduction, and thank you also for the invitation to deliver this keynote lecture at the conference. I very much appreciate it. So now you can all see my screen. Is that right? And you can see my cursor.
Yes, we can able to see it.
Okay. So 1 second. All right. So the title of my presentation is Robust Polymer Materials for Nanofiltration Processes. So first, I will give a brief introduction to KAUST, where I work at the moment, and our membrane center. And then I will introduce you to the research activities and interests of my group. And then we will learn about organic solvent nanofiltration, which is a specific topic within separation science that I'm interested in. And I will give you a couple of examples of different projects and different solutions to be able to do nanofiltration in harsh environments. So we'll see examples which are Bioinspired, we'll see the combination of organocatalysis with membrane separations, catalyst recovery, and cascade reactors. Okay, so here you can see the map. So Chennai is somewhere over here, and we are located here in Saudi Arabia. This is Saudi Arabia, and this is Jeddah. So KAUST is a small university town, very close to Jeddah. Here you can see our university town. This is the university, and this is where we work, where we study, and where we live and do everything. So it's a complete city. You can see the community area where people live. On the left-hand side, you can see the Red Sea, and on the right-hand side is actually the desert. Here is the town center, the campus where we work. We have an innovation cluster. We work closely together with different companies such as Dow Chemicals, Sabic, and Aramco. So some quick facts. You can see that we have about 1,000 students. We are a relatively young university with 10 years of history, and we plan to expand significantly. We want to almost double the student cohort that we have, and we are also planning to increase the number of faculties that we have. And we have a relatively good student to faculty ratio, which is 6:1. Here you can see the different students. We are a postgraduate university, so we have MS students, and the majority of our students are actually PhD students. We have a good balance of male and female students, and they are from all over the world. We have different research centers that you can see here, and the research center where I work is called the Advanced Membranes and Porous Materials, which belongs to PSC, the Physical Science and Engineering division. Okay, so here you can see two pictures. This is actually KAUST, our city, and here you can see the research buildings. I'm actually located in this building. This is where my office is and my labs. And this is another view. Again, this is the building where I'm located. That's our library. Okay, so research areas. Organic solvent nanofiltration, catalytic membrane reactors. Basically, all of these topics that you can see here that we focus on is related to the sustainable and green separation processes using different type of membranes and adsorbents. And we follow a bottom-up approach. We start designing our processes from scratch, including chemistry. Then we develop new separation materials, and then we apply them in chemical engineering processes. So in a nutshell, the group is focusing on sustainable separations through a combination of polymer chemistry, material science, and chemical engineering. So first come first, what is organic solvent nanofiltration? So membrane separations, the objective of membrane separations is to be able to separate different solutes A from B. And the nanofiltration range actually covers the 100 to 2000 gram per mole solutes. So these are relatively small molecules, and usually this molecular weight range is useful for the separation of petrochemicals and pharmaceuticals, fine chemicals. So due to the recent improvements, now we have tighter membranes, we have more stable membranes, and they can be reproduced to a much higher extent than before. So these advancement in membrane science actually translates to the advancement of membrane technology through new applications. So what we are going to look at today is how to develop new types of membrane materials that are more robust, more reproducible, and can provide or enable new applications. Okay, so the first example is about bioinspired membranes and membrane supports. So here you can see a graphic summary of these projects that I'm explaining to you. We use different naturally sourced materials that you can see here to fabricate new membranes. So the idea is that you take a membrane support. You can see here the different polymers and their structures that are used as membrane supports. And here you can see the different materials and their origin, either from mussels, trees, fruits, onion, and so on. So here are the secondary interactions between the polymer material and the coating. So here you can see the general procedure that we follow. You take a substrate, you prepare a membrane on it, which is a very loose nanofiltration membrane, an ultrafiltration membrane, and you use this biophenol coating to close the pores of your membranes and therefore bring it down from a loose nanofiltration or ultrafiltration to a tight nanofiltration membrane. And the different supports that we tried are not necessarily green or sustainable, but the coatings themselves are sustainable. The usual way to stabilize membranes, to be able to use them in organic solvents in harsh conditions, is through cross-linking. And cross-linking agents are very harsh chemicals that can damage the environment. They are toxic and flammable, so it's quite difficult to work with them and undesired. And this is why we decided to develop new membranes that are based on these natural resources. So here you can see a comprehensive table that shows the different substrates here. These are the different polymeric substrates, and these are the different materials that we coated on them. And then we assess the performance of these membranes. So before the performance, we looked at the characterization. So we used different material science techniques to gain an understanding of the different materials and the different coatings. What I would, instead of going into all the details about each individual data, I will just show you all of these characterizations and just focus on the main message. So here you can see that the surface of the membranes are quite smooth, and if you look at the cross section, then you can see the huge macro voids in the membrane structure, and we have a very dense support on the top of the membrane that is the active layer. So in general, we can say that we have a similar characteristic for all the membranes, independently of the polymer and the coating. And the coating increases the hydrophilicity of the membranes, and the surface roughness decreases. Okay, so here you can see the actual performance measurement of the different membranes. So again, instead of going through all the data here that we gathered, just imagine that here you can see the permeance, which is giving you an idea about the throughput of the membrane, how quickly you can filter things. And in red, on the second y-axis, you can see the MWCO. This gives you an idea about what you can separate with the membrane, A and B, the two solids. So what you can see here is we have values all over the place, basically. Okay, so we have lower values, we have higher values, and it changes with the different type of coating materials, natural materials that we use. So, and here you can also see the different coating materials, and you can see that the data changes quite drastically over the different membranes. So overall, what we can conclude here is that the use of the biophenol coatings allow us to fine-tune the performance of the membrane. Okay, so the most important is that if you have a given application and you want to separate A from B, then by using this technique, you can fine-tune the separation performance to achieve the best results. And another way of gaining control over the performance of the membranes is by using Bioinspired interpenetrating polymer networks. So in this idea, again, we wanted to break conventions and move away from the traditional cross-linking of membranes, and we explored growing an IPN. So this is called IPN. Growing an IPN network within a polymer framework, and we hypothesized that this will result in a harsh or a stable membrane that we can use in harsh environments. So the technique is to blend together in a dope solution your original membrane material, in this case it is PBI, and blend in the monomers of dopamine. Then we do the phase inversion, where the membrane actually forms in water. And the next step, or two steps, is to initiate the polymerization of the dopamine monomer. And these are the monomers that are randomly distributed inside the membrane. And during the polymerization, you get polydopamine that covers the membrane. So this is basically a blend where you have two different polymers. The black one is the polydopamine that is cross-linked by itself. And we have the linear chains of PBI represented in orange. Here you can see the chemical structure of PDA, the polydopamine, and the PBI, and how they are interacting through secondary interactions, hydrogen bonding. Again, we did characterization of the membrane, and we looked into identify. Can you hear me? Hello?
Yes, sir.
Okay, great. So yes, here we looked at the TGA coupled with an MS to be able to identify whether we really have this polydopamine growing inside the membrane. And here you can see the two spectra of the different materials, and we managed to identify the PDA here with the MS. So this is just the data behind it. So then we looked at the characteristics of these membranes, and you can see that as you increase the in situ polymerization time of the polydopamine, then you get different characteristics of the membrane. So we looked at the contact angle, we investigated the PDA content, the growth rate, pore volume, surface area, and so on. And what you can see here is that when you move from membrane 1 to membrane 2, then membrane 3, basically you're increasing the polymerization time going from left to right. Then you have a self-acceleration of the polymerization of your PDA, and you increase the mechanical stability of your membrane. And here you can see the stability of the membrane expressed as a percentage weight loss of after DMS treatment. So you can see that membrane 1, 2, and 3, which are PDA coated, are extremely stable, and you have a very small percentage loss of the material, while without the IPM, you lose all your material, everything is dissolved. So basically we managed to achieve a very high stability membrane by doing an IPM type of membrane fabrication. And here you can see the results. So we tested these membranes again to be able, whether it's to confirm whether it's able to separate A and B. So this is about the selectivity, and then we looked at the permeance, about the throughput of the membrane. And here we managed to find literature data that is represented in gray asterisks. And what you can see here is that the higher the permeance, the better. So you can see that all of our membranes, 1, 2, and 3, perform quite well compared to the literature. And there was only one membrane that had outstanding performance in the literature, way better than any other literature values or our values. We also investigated the effect of temperature that you can see here in these two graphs. And we noticed that with the increase of temperature, the pores are opening up, probably due to membrane swelling. So you get a higher permeance with higher temperature, and at the same time you get higher cutoff, which means that the membrane is actually becoming looser for opening the pores. And the next step was to investigate whether we can prepare stable membranes without any cross-linking. So in this project, we were looking at ion stabilization of membranes. That was one of the hypotheses that we investigated. And the other one is whether we can achieve a higher throughput, a higher permeance, if we employ pins. Okay, so PIN stands for polymers of intrinsic microporosity. So here you can see examples of these structures. And these materials, for instance, PIM1, it's a linear polymer that has an extremely high surface area. It's about 700, 750 square meter per gram. So it's assumed that if we incorporate these polymers into the membrane, then we're going to have a high throughput. And to be able to, but the initial one here, this is soluble. So that's a key point here, that when you use the originally reported PIN, it's soluble, which means that the membrane is not dissolved in the soil.
Dr. Gyorgy, there's a small noise from your background, like the audio. Slight noise is coming.
Okay, 1 second. Is it better now, or is it the same? Can you hear me now? Is it better? Can you hear me?
Yeah. Now it is better. Please go ahead. Yeah.
Okay, great. Thank you. Okay, so we had to make this membrane stable in solvents. So because of that, we had to do some chemical transformations, and eventually we prepared this salt, which shows high stability in organic solvents. Okay, so again, we did the characterization of the material. You can see here the FTIR results. We looked at also solid state NMR and AFM, SEM. You can see a similar structure that I showed before. You have macrovoids here, and on the top you have the dense layer. And here, this image was taken with a technique called AFM IR. So here, basically, these lumps represent the height of the material, and the color represents the intensity of a selected peak in IR. So what we were looking at here is whether we have a clustering of one of the polymers compared to the other one. And this image was taken at high loading of the PIM, where it actually started to aggregate and cluster. Okay, so this structure was avoided, and we couldn't go at a very high PIM content due to clustering effects. Then we looked at the performance. We see with the BET surface area that we managed to increase the surface area as we incorporated more PIM into the material. And then we were interested in the chemistry of the polymer and the stability of the membrane. So what you can see here is that at low pH, you have both the PBI and the PIM protonated, and then you get a stable membrane. There is no loss when you're soaking it into these aqueous solutions. When you go to the very high pH value, there you get deprotonated polybenzimidazole, and you get a neutral PIM. So in that case, again, we have very stable membranes. However, in a mid-range pH, when we go from 6 to about 10, and for the other polymer, let's say 9 to 10, then what happens is that PBI is in a neutral form, and only one of the amine groups of the PIM is protonated, and then this allows the membrane to be soluble. And therefore, here you can see that in this pH range, you're losing your membrane when you're performing a separation. So these membranes should be used at lower or higher pH. Okay, so here you can see the permeance that we compared, and again the MWCO for the separation in different organic solvents. So these membranes were stable in polar solvents such as acetonitrile, methyl PHF, DMF, DMSO, or polar clean. Okay, so one of the other key aspects that is important for membranes is whether you can use them at high temperature or not. So what we investigated is the effect of temperature on these two performance metrics, the selectivity and the throughput. So here we did a sequence, actually 4 of it. So we started with sequence 1, where we increased the temperature step by step. And then in sequence 2, we decreased the temperature back to room temperature. And again, we went up, and then we decreased back to room temperature. And here you can see the effect on the performance. So the conclusion here is that there is an initial compaction and change in structure at the beginning of this thermal treatment. So when you increase the temperature first, you get this performance profile, but when you decrease it, then you don't get it back. You get basically a lower performance. But after that, this performance remains stable. Okay, so the most important for a membrane is to be reproducible. You always get the same data. So what we realized here, if we can do a treatment at different temperatures, then we can fine-tune the properties of the membrane. And this is true for the selectivity here as well. Okay, so the next work that I'd like to introduce is about the use of graphene oxide blended with polybenzimidazole to achieve high stability membranes. Okay, so here you can see the chemistry. Again, we have polybenzimidazole as the matrix for the membrane. And in the first step, we modify the surface of the membrane to introduce these hydroxyl groups. And after that, we managed to use graphene oxide, which is loaded with hydroxyl groups, among others, and this isocyanate crosslinker to get this structure. So what you can see here is that using this crosslinker, you can cross-link the polymer chains. You can also attach or graft the graphene oxide onto the polymer, and you can also cross-link two graphene oxide sheets. So due to the high cross-linking degree, again, we would expect that these membranes will be highly stable. And in the literature, it was observed before that the addition of GO into membranes usually increases the hydrophilicity and increases the throughput, increases the flux or permeance. So again, we looked at the characterization of the membrane after this covalent anchoring. So why is it important that we use covalent linkage? So the literature before basically blended GO into the polymer matrix, prepared the membrane and used it. But in long term, the GO can leach out. The polymer chains usually rearrange, and it gives way to the GO to escape from the membrane, contaminating your product and also decreasing the membrane performance. So to avoid this deterioration of the membrane, we hypothesized that covalent anchoring would be the solution. It is notoriously difficult to follow the GO distribution in polymer matrix. So we came up with a simple solution that you can see here in the first row. We used optical microscopy. And as you can see, the GO flakes are actually shiny. And this is where you can see then how well your GO is distributed. Otherwise, you can see the surface of the membrane, which is quite smooth, and you can see the cross-section, which is a typical ISA or asymmetric membrane structure. We looked at the carbon solid-state NMR to verify the presence of the cross-linking and also the presence of the GO. Okay, so here you can see the final results for these membranes. We prepared a series of membranes and then we investigated what is the effect of cross-linking, what is the effect of the introduced hydroxyl groups, and what is the effect of the graphene oxide. So here you can see again that as you change the constituents of your membrane, you can change the permeance. And at the same time, the rejection can also change. And there is a trend. If you look at the graph in the middle, you can see that the rejection profiles, they actually form different clusters depending on what type of membrane you're using. So this is the benchmark membrane at the bottom. And then you can see cluster number 1 in yellow, which is the non-crosslink membranes, which are a little bit tighter than the benchmark membrane. But if you do the cross-linking with the isocyanate, then you get this cluster, the green one, which shows that this is a much tighter membrane. So again, you can fine-tune the performance of the membrane, and you can achieve really tight membranes. So one of the objectives in nanofiltration is to be able to produce membranes with high flux that also have high rejection. And we tested these membranes in different organic solvents to prove their stability over 2 weeks of continuous filtration. And these were tested in both DMF, it was tested both cross-link and non-cross-link to prove that both membranes can be stable in some given solvents. And here we observed something unexpected. So if you look at this data set, then all of these solvents are fine with the cross-link membranes, but the non-cross-link membranes usually are not stable in polar aprotic solvents. And here you can see DMF, which is a polar aprotic solvent, and nonetheless, the non-cross-link membrane, the green one, was also stable and showed more or less similar rejection profile as the geo-incorporated cross-link membrane. So here, what we assume happened is that the geo itself cross-linked the polymer network. So we know that graphene oxide has epoxide groups, and they are highly reactive. So what we assume that happened is that the epoxide group reacted with the amine group of the PBI, and to a certain extent cross-linked the network. And this is why the membrane became stable in DMF. Okay, so how much time do I have left? Because I wanted to introduce one more project, but I'm not sure if I still have time for it.
Yeah, you can take 5-10 minutes, no problem. Your convenience, Dr. George.
Okay, okay. So then let me talk about a slightly different project. This is about organocatalytic membrane reactors. So far, what we have seen is that you can use a membrane and you can separate, let's say, A and B. Okay, you have a mixture of solutes, one goes through, the other one doesn't go through, so you separated them. But what if we could add a catalytic site onto this membrane, polymer membrane, and then you have your reagent and substrate in the feed solution, and as they go through the membrane, then eventually they form your product. So at the same time, you can do separation and you can do reaction. So again, we turn to polybenzimidazole, and we looked at today is how to prepare robust membranes that you can employ in organic solvents or extreme pH, very low pH, or very high pH. And we looked at polydopamine, which is derived from dopamine, and we looked at another kind of different naturally occurring materials to be able to achieve these high stability membranes. We also looked at another example where we used GO graphene oxide to increase the stability of the membrane, increase the permeance of the membrane, and the last example showed how we can incorporate a traditional organocatalyst covalently linked onto the polymer substrate, and then use this membrane in a catalytic membrane reactor where you can do the catalysis using the incorporated organocatalytic structure, and at the same time separate any impurities or remaining substrate from the solvent and from your product, and how you can recover this product. So overall, these were a couple of examples from my group that shows how we try to incorporate green chemistry and green engineering into the field of separation technologies. So I would like to thank KAUST and the University of Manchester for supporting many of these projects. And again, thank you for your attention, and thank you for giving me this opportunity to present some of our exciting works to you.
Yeah, Thank you very much, Dr. Gyorgy Szekely. It was really a wonderful talk, and you have covered many points. I'm sure our students will be much benefited based on your talk. I have a few basic questions. So before that, let me open the session. So in case if the faculties and students have any queries who joined us, can ask. Otherwise, I can. After that, I will ask the questions which the students have texted. Yeah, yeah. Now the session is open. Please go ahead and ask your questions.
Sir, I'm audible.
Yes, yes.
Which type of membrane can be suggested for application in food industry, sir?
In food industry, it really depends. So in the food industry, most of the solutions are aqueous solutions. So you don't need a very high stability. So it really depends on what is your stream that you're trying to separate and what are the solutes that you have. So in some cases, you need to do microfiltration when you want to separate out particles. And on very small scale, if you have any specific impurities, then you can use nanofiltration as well.
Thank you, sir. Sir, one more question. Sir, in your presentation, you said about biophenol coating used in membrane. If you use
Yes.
that membrane in food industry, whether biophenol affect food nutrition?
Is it, sorry, what was that?
Yes, sir.
I lost the question.
Sir, you said in your presentation for biophenol coating used in membrane. If you use that membrane in food industry, whether biophenol
Yes.
affect food nutrition?
That I'm not sure about. I'm not sure.
Thank you, sir.
Thank you, sir. There are a few more small questions from the students. One student have come up with a very like basic question about cross-linking and what is the use of cross-linking in membrane.
Okay, so basically membranes are made out of linear polymers. Okay, and these linear chains, they get dissolved easily in organic solvents. So if you prepare a membrane and you immerse it into an organic solvent, then it will vanish, it will disappear. So you cannot do any separation with your membranes anymore. However, if you prepare this membrane and cross-link these linear chains, then it becomes insoluble. So after that, you can easily use it in any organic solvents or extreme pH because they gain stability. Okay, so the idea and the objective of cross-linking is to make the membrane stable in harsh environments.
Okay. One more quick question. Another student, he asked about the stability of the membrane. Like you have shown about dissolving the membrane in solvents like DMF. Is there any other way to check the stability of the membrane, or usually the standard procedure is to dissolve the membrane in the solvent to check the stability?
Yes, during the stability checking, we always use different kinds of solvents because they help you to identify the solvents in which you can actually use the membrane. So if let's say you have a stream with DMF, then you need to test the stability of the membrane with DMF, because otherwise you don't know whether it's going to dissolve or not. So we always do them in solvent, and there are different ways of checking to check the stability. If you immerse it into DMS, for instance, and it vanishes, then it's obvious that's what it's soluble and we cannot use it. But nonetheless, if you immerse it and you still have a membrane material, it doesn't mean that actually convert exactly separate something. It's not modified. You can have different secondary interactions with the solvent and the membrane. So it's very complicated system. You can also look at the
Can you slightly correct your microphone? Like some echo is coming in.
Okay, is it better now? Can you hear me now?
Yeah, better. Please.
Great. Yes, so you can do a swelling test, and then that's one way of testing the stability. And you can also measure the weight of the membrane before and after solvent treatment. And if you get a constant weight, then you have a stable membrane.
Yeah, thank you very much. Thank you very much for once again for spending your valuable time in addressing and giving an invited talk in our conference, ICDAMS2020. We really appreciate your efforts in spending time here, Dr. Gyorgy, and looking forward to further collaboration and other things like maybe with KAUST, what sort of collaborations we can look into. If you can let us know, we can definitely collaborate, make a collaboration between both our university, Saveetha and KAUST. Looking forward to that.
Sounds great. Let's keep in touch. Thank you very much.
Thank you, Dr. Gyorgy.
Thank you.
Yeah, good. Yeah, bye.
Thank you, sir.
Thank you.